I welcome you all in our today's session. In this session, we are going to study the design of FIR filter using windows. Basically, a digital filter is a linear time invariant discrete time system. The term FR filter and IR filter are used to distinguish filter types. The FR filters are non-recursive type of filters, where the present output depends on the present input sample and previous input samples. Whereas the IR filters are recursive type of filters where present output sample depends on the present input, past input and the output samples. Here our main focus is on FR filter design, where we are going to use windows for the design of FR filter. In many of the digital processing applications, FR filters are preferred over the IR filters. The main advantage of FR filter is it is always stable. FR filter with exact linear phase can easily be designed. Also, the FR filters are realized in both recursive as well as in non-recursive structures. The FR filters are free from limit cycle oscillations when implemented on a finite word length digital system. There are many excellent design methods are available for the design of FR filter. As there are advantages, there are some disadvantages also. While implementing the narrow transition band FR filter, it becomes very costly as it requires more arithmetic operations and hardware components such as multipliers, adders and delay elements. Also, the memory requirement and execution time is very high for FR filter design. The design of FR filter has different methods. In this session, we are going to study the window technique. The desired frequency response HD of e raised to j omega of a filter is periodic in frequency and can be expanded in the Fourier series form. The resultant Fourier series is given by HD of e raised to j omega is equal to summation from n is equal to minus infinity to plus infinity HD of n e raised to minus j omega n. Also, the impulse response HD of n is given by 1 upon 2 pi integral from minus pi to pi h of e raised to j omega into e raised to j omega n d omega. One possible way of obtaining FR filter is to truncate the finite Fourier series at n is equal to plus minus n minus 1 divided by 2, where n is the length of desired sequence. But this truncation of Fourier series results in oscillation in the passband as well as in the stopband. Now these oscillations are due to slow convergence of Fourier series, and this effect is known as the Gibbs phenomenon. To reduce these oscillations, the Fourier series coefficients of a filter are modified by multiplying the infinite impulse response with a finite weighing sequence W of n, which is also known as a window. W of n is always equivalent to W of minus n, which is not equal to 0 for modulus of n less than or equivalent to n minus 1 divided by 2, and it is equal to 0 for modulus of n greater than n minus 1 divided by 2. After multiplying window sequence W of n with HD of n, we get a finite duration sequence H of n that satisfies the desired magnitude response. The H of n is given by HD of n multiplied by W of n. for again modulus of n less than or equivalent to n minus 1 divided by 2, and it is equal to 0 for modulus of n greater than n minus 1 divided by 2. H of e raised to j omega is given by 1 upon 2 pi integral from minus pi to plus pi hd of e raised to j omega into w of e raised to j omega minus theta d theta. The frequency response of the filter h of e raised to j omega depends on the frequency response of the window, that is w of e raised to j omega. Therefore, the window chosen for truncating the infinite impulse response should have some characteristics. The characteristics are described below. The central lobe of frequency response of the window should contain most of the energy and should be narrow. The highest side lobe level of the frequency response should be small, and the side lobes of the frequency response should decrease in energy rapidly as omega tends to pi. There are various windows that can be used to design a FIR filter. So one of the window is the rectangular window. The structure of this window is like a rectangle or a box type, so it is also known as a boxcar window. The equation for rectangular window is given by WR of n is equal to 1 for minus n minus 1 divided by 2 to n minus 1 divided by 2, and it is equal to 0 otherwise. Now here we are considering that there are n number of samples where n is equal to 11. The rectangular window is described here. It has magnitude is equal to 1 for all 11 number of samples, okay, and it is from minus 5 to plus 5. That means minus n minus 1 divided by 2 to plus n minus 1 divided by 2. The Fourier transform of rectangular window is given by WR of e raised to j omega is equal to n minus 1 divided by 2 minus n minus 1 divided by 2 to plus n minus 1 divided by 2 e raised to minus j omega n. If we simplify this, we will obtain sine of omega n divided by 2 divided by sine of omega divided by 2. The main lobe width of rectangular window is equivalent to 4 pi divided by n. The higher side lobe level is 22% of main lobe amplitude, or it is equivalent to nearly minus 13 dB. This is most commonly used window. The second window is the triangular window or Bartlett window. Here the window structure, if you can observe here, the window structure is like a triangle, so it is known as the triangular window. The equation for the triangular window is given as Wt of n is equal to 1 minus 2 into modulus of n divided by n minus 1 for minus n minus 1 divided by 2 to plus n minus 1 divided by 2. The Fourier transform of triangular window is given by Wt of e raised to j omega is equal to sine of n minus 1 divided by 4 into omega divided by sine of omega divided by 2 whole square. The side lobe level is smaller than that of the rectangular window, and that is minus 25 dB. If you observe the main lobe width of triangular window, it is 8 pi divided by n, that means greater than that of the rectangular window. It has smooth magnitude response in both pass band as well as in the stop band, but the transition region is more in case of the triangular window, okay, and the attenuation in the stop band is also less. The next window type is the raised cosine window. The raised cosine window multiplies the central Fourier coefficient of approximately unity and smoothly truncate the Fourier coefficients towards the end of the filter. The window sequence is of the form W alpha of omega alpha of n is equal to alpha plus 1 minus alpha to cos of 2 pi n divided by n minus 1 for n in between minus n minus 1 divided by 2 to plus n minus 1 divided by 2, and it is equal to 0 otherwise. There are three different types of raised cosine window. First one is the Hanning window, second one is the Hamming window, and the third one is the Blackman window. We will see the equation of all these windows one by one. The first raised cosine window is the Hanning window. The Hanning window sequence can be obtained by substituting alpha is equal to 0.5. WHN of n is equal to 0.5 plus 0.5 cos 2 pi n divided by n minus 1, and it is equal to 0 otherwise. The frequency response of Hamming window is given by WH of n e raised to j omega is equal to 0.5 into sine of omega n divided by 2 divided by sine of omega n divided by 2 plus 0.25 sine of omega n divided by 2 minus pi n divided by n minus 1, the whole divided by sine of omega divided by 2 minus pi divided by n minus 1 plus 0.25 sine of omega n divided by 2 plus pi n divided by n minus 1 whole divided by sine of omega divided by 2 plus pi of n minus 1. The Hamming window structure is shown here. The main lobe width is 8 pi divided by n. The magnitude of side lobe level is minus 31 dB. This results in smaller ripples in the both pass band as well as stop band. If you observe the Hanning window structure, the window has magnitude is equal to 0 at the end samples or at the last samples. The next window type is the Hamming window. The equation for Hamming window can be obtained by substituting alpha is equal to 0.54. So the equation of Hamming window becomes WH of n is equal to 0.54 plus 0.46 cos of 2 pi n divided by n minus 1, where n varies from minus n minus 1 divided by 2 to plus n minus 1 divided by 2, and it is equal to 0 otherwise. The frequency response of Hamming window is given by WH of e raised to j omega is equal to 0.54 into sine of omega n divided by 2 divided by sine of omega divided by 2 plus 0.23 into sine of omega n divided by 2 minus pi n divided by n minus 1 divided by sine of omega divided by 2 minus pi divided by n minus 1 plus 0.23 sine of omega n divided by 2 plus pi n divided by n minus 1 whole divided by sine of omega divided by 2 plus pi n minus 1. If you observe the structure of the Hamming window, it is like this. If you observe the shape of this Hamming window, these last samples on both the sides, it has some negligible amplitude. It is just about 0.08. It is not equivalent to 0. That is the difference between your Hamming window and Hanning window. Hamming window has more width than that of the, or more wider than that of the Hanning window. The main lobe width is 8 pi divided by n for the Hamming window. The peak side lobe level is minus 53 dB. And at higher frequency, the stop band attenuation is low as compared to that of the Hanning window. So these are the different windows that we have studied. What we have to do, just we have to multiply our impulse response Hd of n with the window, that is W of n, and it will provide us the required impulse response H of n. Here we have studied the FIR filter with the window techniques. First window is the rectangular window. Second window that we have studied is the triangular window. Third one is the Hanning window, and fourth one is the Hamming window. I hope this video is helpful for your understanding. Thank you.